Okay, in the first video of this whole series, we were given a surface, which was the top half of a sphere of radius 2. We were given a vector field, and we calculated the work done around the boundary, and we got 4 pi. What we want to be able to do here is look at the right-hand side of Stokes' theorem and hopefully get the same answer. Just a reminder of what this looks like. We no longer care about the edge. We do care which direction's up, because we actually have to start calculating a lot of things here. The first thing I want to do is calculate the curl, because that's actually the vector that's going to go there. So let's do that first. Calculating the curl vector. Remember, that's the cross product of two things. So this is going to be I, J, K. Remember, the del operator looks like a vector, so this is the symbol that says the derivative with respect to x of, and then the derivative with respect to y of, and then the derivative with respect to z of, and then we put the stuff in. This should be 2x minus y. This should be y squared. This should be y squared z, like that. And we're going to get a vector. Let's see here how I want to do this. I guess I'd like to write this like a vector. If I cross off the I column and cross off the j column, what I'm going to get, I think, is 2yz. Like that. I'll just double check. Crossing off the I column, crossing off the j column, crossing off the I row, crossing off the I column. I'm going to get the partial with respect to y of y squared z, which is 2yz, minus the partial derivative with respect to z of something that doesn't have a z in it. Great. To do the second one, I'm supposed to put a minus sign, and then I cross off the j row, cross off the j column, and I'm going to get the partial derivative with respect to x of something with no x's in it, minus the partial derivative with respect to y of something that has no z's in it. I'm writing down minus 0. I will correct that thing that makes me feel stupid in just a second. To get the third entry, I'm supposed to cross off the k row, I cross off the k column, and what I'm going to get is the partial derivative with respect to x of y squared, which is 0, and then minus, and then the partial derivative with respect to y of 2x minus y, which is minus 1. So what we're going to get for the curl vector is 2yz, 0, 1. And that's what needs to go right here. And that's what I'm going to put right there. Here we go. Let's see, I think I can get away with this at the moment. Let's go like this, go like this, and I need 2yz up here, and I need 0 and 1. And I'm supposed to dot that with the area vector. Well, how do we get the area vector? Well, we only have one way of finding area vectors this semester. That says if we're lucky enough, right, to have our surface be the graph of a function of the form z equals f of xy, then the area vector looks like minus fx minus fy 1. And by the way, remember, that's just a normal vector of the tangent plane. And we also have to have a dx dy here. That actually turns it into an area vector. But meanwhile, I think that's what I need to calculate, because there's my function. I know that z equals the square root of 4 minus x squared. So here we go. We're going to calculate our area vector out. And I think it's going to be kind of big. I need the partial derivative of the square root of 4 minus x squared minus y squared. When we take the derivative and then change the sign, I believe we're just going to get this x over the square root of 4 minus x squared minus y squared. When we take the derivative with respect to y and change the sign, I believe we're going to get y over the square root of 4 minus x squared minus y squared. And then we're just supposed to have, 1 like that. And then dx dy. And that's going to be our formula for dA, which needs to go up here. So I'll put it up here, and we'll see what we can do with this. This is going to be x over the square root of 4 minus x squared minus y squared. That's x. Make sure that looks like an x. Good. And then I need y. Well, you see, it's not going to matter. Over the square root of 4 minus x squared minus y squared, and then 1. Just like that. And then dx dy. So we're moving closer to something that looks like an integral, as opposed to something that looks just like this. It looks very symbolic. Although by the time we leave, we really need to be able to look at that and say, this is where this comes from, and this is where this comes from, etc. Meanwhile, I'm going to take the dot product of those two things. And so I'm going to get integral s. And so what I'm going to get looks like 2xyz over the square root of 4 minus x squared minus y squared plus 0, because that's 0 times the y stuff, plus 1. And then we still have our dx dy. And now we have the same kind of problem as we had with the flux integrals, is that this still has a z in it, which I don't like because my variables are only supposed to be x's and y's. And I don't like s because s is actually the top half of a sphere, and that also has z's in it, so we need to fix both. We can fix the z easily because it's just the square root of 4 minus x squared minus y squared. And we're just going to talk our way through this one at the moment. Remember that z is the square root of 4 minus x squared minus y squared. And when I put that right here, the bottom's going to cancel with the top, and that's all I'm going to be left with. So what I'm going to have is just 2xy plus 0 plus 1. How about just plus 1? Now dx dy, right? Now this isn't just smushing. I mean, the thing about it is my variables are now just x's and y's. So what we want to do is look at the points we were using if we were only using the x's and y's. Well, remember what this looks like. Here's our sphere, right? If we only look at the points x and y, so only the points in the xy plane that we use to actually graph the sphere, it's just going to be that circle of radius 2 down here filled in. Now, by the way, they call that a disk. So when you see the word disk, you know that's just a filled in circle. So that's actually the domain of integration, which is nice. That tells me, by the way, that if I'm going to do this, I'm going to want to use polar. I mean, maybe I'll get something weird that I don't like, but it's better than actually having, the square root of 4 minus x squared minus y squared in a limit of integration. So I'm going to turn this into polar. Remember how we find this, right? We start drawing rays, right? The rays enter the region when r is 0. The rays leave the region when r is 2. Like this and this. So this is just going to go from 0 to 2. In order to fill in the disk, we have to use all the thetas from 0 to 2 pi. So that's not bad, like that. Now I need to remember that x is r cosine theta, y is r sine theta. That's correct. Yes, so what I'm going to get is I'm going to get 2 r squared cosine theta sine theta. And let's just double check that. That's what you get when you multiply 2 times r cosine theta times sine theta. Good. Plus 1. And then r d theta. Now this is one of the few times we're actually going to try to do the integral because we want those two sides to actually equal. And remember, I think we want to get an answer of 4 pi when we're done, so I'm hoping. So we're going to start evaluating this integral. Here we go. I'm going to go from 0 to 2 pi. In order to evaluate this integral, I really need to multiply that r all the way through. So I'm going to get 2r cubed cosine theta sine theta plus r dr d theta. And now let's see here, haven't done the integral yet. This is still going from 0 to 2. So now I take the antiderivative. I'm going from 0 to 2 pi. The antiderivative there is going to be, I think, r to the 4th over 2. That's correct. And then I have cosine theta, sine theta, don't have to worry about that stuff yet, plus 1/2 r squared, like that. I think that's right. This is just going to be from 0 to 2, and then d theta, like that. let's see here, what do I want? I want to just plug in. So I'm going from 0 to 2 pi. When I plug in 2, I get 16 over 2, that's 8. That's going to be 8 cosine theta, sine theta, like that. And when I plug in 2 there, I get 2. Yes, is that right? I think it is. And then I get that d theta like that. And what we're hoping is that we can do this integral. I think we actually just did this one a minute ago. I'm thinking an antiderivative of 8 cosine sine is 4 sine squared. I think minus 4 cosine squared would also work. But 4 sine squared I think looks easier. So I want to go that from 0 to 2 pi. Antiderivative of 2 is just 2 theta. Is that right? I want plus 2 theta from 0 to 2 pi. When I plug in 2 pi into theta, I get the same answer that when I plug in 0 into theta. So I get nothing here. This is just going to be 0 when I plug it in. When I plug in 2 pi into theta, I'm going to get 4 pi. When I plug in 0, I'm going to get 0. And so we can see that the answer should be, there we go, 4 pi, which is exactly the same answer we got the first time. Neither one of these integrals is a whole lot of fun. But at least we've showed that it's the same answer. And that's actually the only thing we want to do here, is get used to the context and make sure that when we calculated both the line integral and the surface integral that we got the same answer, and we did.